Ну что ж, дорогие коллеги.
Well, dear colleagues, just as prearranged and agreed, we start at 4 o'clock our last panel discussion for today, which is also dedicated to the application of remote sensing data. And we are looking forward to a very interesting report presentation by David Critchley, who will talk about satellite bathymetry.
And also thank you to all my new Russian friends for making me feel so welcome in the last couple of days here. I suppose you're wondering what we're talking about with satellite bathymetry. We're in a land mapping forum. The title says Digital Photogrammetric Technologies. That we increasingly see an overlap between sea mapping and land mapping. I suppose this started about 10 years ago with the bathymetric LiDAR systems. I set up a company 5-6 years ago for bathymetric LiDAR, and this was the crossover between sea mapping and land mapping. Before all of the sea mapping was done by boats with multi-beam or single beam. And then with the LiDAR, we had green LiDAR for the seabed mapping, red LiDAR for the topographic, and an image sensor as well. So all of a sudden, 8-10 years ago, we were able to create a seamless map from the seabed onto land. And this now is transformed into the ability to create seabed maps from satellite imagery. And my presentation today is more about the case studies in the projects we've done in the last year, all over the world, mainly using WorldView 2 imagery. Okay, why satellite bathymetry? Why is this technology so exciting? Well, first of all, we estimate it's between 5 and 10% of the cost of traditional methods of boats and aeroplanes. You know, before when we had the LiDAR, if we had a project in Taiwan, for example, it would cost $300,000–400,000 just to mobilize an aircraft to do a small survey. This is not in the interest of the client or interest to the contractor to spend so much money and create so much pollution in mobilizing an aircraft. Both multi-beam and LiDAR are very slow technologies for seabed mapping. Normally with bathymetric LiDAR you collect about 10 square kilometers per hour for high resolution data. With satellite we can cover very, very large areas in a very short space of time. Doing projects around the world, I'm based in the Middle East, trying to get permits for aircraft is a nightmare. It can take you 6 to 12 months. You need 50-60 documents supporting your permit, and a lot of the time you do not get the permit to carry out your operation. You know, there's also problems with borders. If you've got a project to do a seabed map, for example, in United Arab Emirates, how do you get an airplane or a boat to operate along the borders of Qatar or Saudi Arabia? You cannot get these permits. So the satellite bathymetry is a borderless solution. It's carbon neutral. There's no hazards to marine ecosites. Boats are very pollutive and they can cause quite a lot of damage to the coral reefs, etc. So there's a health and safety issue as well. There's been incidents around the world in the last 20-30 years where boats have crashed onto reefs, and there's been loss of life because they're operating areas with no charts or no information, where there's no health and safety issues with satellite bathymetry. In the past year and a half, we've completed around 20 projects now, and we think the technology is proven. We know it's round about this. It operates in the same or similar parameters as LiDAR and can operate and offer similar results. And we think it's an incredible, fast, cost-effective, efficient tool for coastal zone management, marine habitat mapping and bathymetry. Okay, the application today, who is interested in this technology? Well, of course, the hydrographic people are very interested. We know there are many, many areas in the world where there is no nautical charts available. or if the charts are available, they were created 100, 150 years ago by lead line, i.e. throwing a piece of a lead weight over the side of a boat to determine the depth of the sea. In the UK, there's still areas of uncharted territory all over Europe, all over the Middle East. There's lots of areas never been surveyed in the sea. For the military, there's several aspects of interest there. Amphibious landings, where can we land boats in foreign territories, for example, and which also leads on to national security applications. Environment is very interesting because when we carry out this process of bathymetry, we create two products in the same process. We actually classify the sea bottom during the same process as creating the bathymetry. So environment agencies around the world are very interested in the habitat mapping, seagrass, coral, sand, mud, rock, etc. EIAs, this is short for Environmental Impact Assessment, and we're doing quite a few projects, especially in the Middle East, for power stations, nuclear power stations, for desalination plants, etc. Also for building new ports, what is their approach? Are there any reefs that are going to be in the way of the incoming boats? Engineering is a big area for us, dredging, port design and approach, feasibility studies. Where can we put a port? Can the port go here? Can it go there? What's the most cost-effective, efficient way of positioning a port? Oil and gas is very interesting. There's a big interest for oil and gas companies to do environmental impact assessments, understand the location for pipelines to be built and to come onto land, and for natural resources. And we're looking at a project at the moment in Bahrain where they need to understand where they have sand. Now, it might sound funny, the Bahrain is looking for sand because it's in the desert, but they need to know where certain types of sand are on the seabed for dredging for construction purposes. I'm not technical. I'm going to give a very brief explanation of how it might work and what we use, but for today we're going to be talking about the case studies, about the applications and the results we've found more than anything. So we know we can do satellite bathymetry from other satellite data, mainly potentially Rapid Eye or Landsat, but the most interesting satellite for us is WorldView 2 data. And there's two main reasons for that. One is the resolution, so we can get a high resolution, high accurate product. The second is the fact that it's multispectral and has this very, very special coastal band with the big blue arrows pointing to that band there. And the next series of slides shows you what an image over the sea looks like with the different bands. Okay? These slides are kindly given to me by Digital Globe. So when we are working with the reds over here, we don't see anything in the sea apart from the vegetation. When we use the reds, we don't see much again. The yellows and the reds, we don't see much. But the water column now starts becoming more transparent. And as we go to the blue, we can start seeing the seabed. And then with the very special coastal blue, it allows more spectral analysis of the bottom, i.e. almost creating more transparency of the water column to allow us to map the seabed. And of course, you can make a height map from the data. During the process, one of the big issues we have is not to do with the water, but actually to do with the atmosphere. Atmospheric correction is very important to us. And there's actually two correction processes, one for the atmosphere and one for the sea. So this is Rottnest Island over Australia, and I'm just showing you the difference between the corrected image and the uncorrected image. This is the kind of image we can now work with and use spectral analysis to map the seabed for bathymetry and for classification of the habitat. In terms of the technical specification, the positional accuracy is similar as though you were going to be creating an ortho from WorldView 2 data, it's 4 or 6 meter positional accuracy, CE 90. We'd probably be able to get more accurate than 4 meter. We'd probably head towards 2 meter, but when we're moving away from the coast or we're working in remote areas, we don't want to really promote much more than 4 meter positional. The height accuracy is interesting. When you're working with LiDAR or multi-beam, you have a definitive height accuracy. So for LiDAR, for example, you can say, okay, the height accuracy down to 30 meters of water is going to be plus or minus half a meter or plus or minus 1 meter. But with satellite bathymetry, we have to say it's 10% of depth. So at 10 meters of water depth, we are operating around about plus or minus 1 meter in good water quality. Later on, I'm going to show you when we get to bad water quality, where there's more turbidity in the water and there's more vegetation and organic matter, we lose accuracy. And I can show you later how we report that in our findings. Pixel size, point spacing is 2 meter or 4 meter grid. Of course, all clients would prefer the highest grade, would prefer a 2 meter grid. But what we found with the 2 meter resolution data was that there was a lot of noise in the data, just like LiDAR, a lot of spikes in the data. We have a lot more sound data when we put 4 pixels together and we create a single point from them 4 pixels. When we do a project, we talk to the client, do you want a 2 meter grid or a 4 meter grid? We can talk to the client about that. In terms of depth penetration, we operate at something called 2 times secudisc now, because you're all from the land mapping arena. Maybe you've not heard of a secudisc. Well, we have all this wonderful technology, LiDAR, satellites and algorithms, but at the end of the day, we rely on a white plastic disc that we drop off the side of a boat. And when the white plastic disc disappears, we measure the depth and we can operate 2 times that. So this is really, we operate, the easiest way to explain that is we operate at around about the 2 times the visible light. So when the visible light disappears at 5 meter, we can create bathymetry and seabed classification at 10 meter depths. The maximum depth we've reached so far is 27 meters in very clear waters in Caribbean. We've reached 20 meters in the Gulf, in the Arabian Gulf. And we think in the Black Sea or the Caspian Sea, we think we can reach 12 to 15 meters, but we need a trial to confirm this. Data products are almost identical to the LiDAR or multi-beam, as we give an ASCII XYZ file. And when we are creating the ASCII file, the Z value, the height value in the, for the seabed, we can create this, we can refer the Z value to the ellipsoid, or we can refer it to tidal data. In the hydrographic world, they operate sometimes to what's called lowest atmospheric tides or mean sea level or something like this. It depends on the data. If we're going with a hydrographic client, they'll want a tidal reference. If we're talking to an engineer who's used to the land, and we refer everything to the ellipsoid. WorldView 2 imagery, of course, metadata. With seabed classification, we can offer a geotiff and database, geospatial database of the habitat content. We provide a quality map. We tell you where the data is good or not good. And this is very important because it really affects the accuracy. Okay, I've got about 3 or 4 examples of case studies we've done so far. I've chosen these because of the findings we've been able to compare it against existing data, for example. The first project we did was about a year ago. The trial was with UK Hydrographic Office in the Caribbean. This is over a test area where they have multi-beam and LiDAR data. We reached 27 meters, but the project was not so good. There was a lot of noise in the data, and the project was actually rejected by UKHO. And the reason being is this area over here, we had a lot of noise, and the data was actually unusable to the UKHO. And this is mainly because In these areas here, the red areas, there was vegetation, and the algorithms that we used to create the depth were creating what the UKHO call unsafe data, i.e. we were reporting deeper than it actually was, which meant it would be very dangerous for boats. So we went away and we were able to learn from this project. This was a very early project. And the majority of the project we thought wasn't so bad. The blue areas indicate that we were better than 1 meter. The yellow areas were where the the seabed went from 20 meters to 27 meters very sharply. So the UKHO didn't like it. So we've gone back and we've now corrected these issues, and majority of projects that we are doing are very good. I would say around about 90% of the projects we do are meeting the criteria that we're setting. This project is Wexford in Ireland. The Geological Survey Ireland are very reputable in the world of bathymetry. They're one of the best funded agencies in Europe for creating bathymetric maps. And this project was to do to compare against multi-beam, single beam, and even LiDAR in a test area. And in terms of issues, there's a river here. This is a river where a lot of turbidity was coming in to the area, and we struggled to get good quality data around the river mouth. But if we look at the quality map, the green area means that the data is extremely reliable and very good. The yellow we indicate as limited liability. The data needs to be approached with a little bit of care. But don't forget, all these projects that we do, we have no ground truthing. We have no proof of what we're doing. And so what we have to tell the client is, when we do a trial like this, is, okay, this data is good, this data is, we have to treat with some care. Red areas, we have very little confidence in the data. Now, this was even if you use LiDAR, this red area, you would not be able to get any data. You'd have to infill with echo sounding, because the water is so turbid, you cannot get data. I know you're not going to be able to see the results, but this is a comparison carried out by the Geological Survey Ireland, and what they did, they sailed a boat from here all the way out here with a multi-beam system. And what they found was that the data in the red areas that we said was unreliable data, the data was 2 or 3 meters out. It was unusable data. But the majority of the data here in the blues and the purples, it was almost zero error to the multi-beam echo sounder. It was better than ½ a meter in most areas. And over here in the green, we started going to plus or minus a meter. And this is mainly because where the water started going towards 15 meters and more in depth. So we say plus or minus 10% in depth. We would expect this green area to be around about a meter and a half comparison. Okay, 3 minutes left. I'll go quickly. Amphibious landings. The importance now of understanding the connection between the seabed and the land. Here you can see we've overlaid our data onto Google Earth, and this allowed navies in Europe to work out where they could do amphibious landings on the boats. Same project. Manama in Bahrain, comparison of the data. Here, this is against multi-beam data, 12 years old, with between 0 and 1 meter in 5 meters of water. A very favorable survey. In terms of additional products, seabed classification is extremely important, and we can produce this simultaneously with the bathymetry. For example, in good clear waters around Mexico, we can create 16 classifications, but in Gulf, where we have more turbidity and a little bit less life, we can only create 6 classifications. We use spectral analysis to determine the seabed bottom. For example, the dashed line across the top can be found using most of the bands in the World View 2, whereas the vegetation, we have to use the near infrareds and the red edge. Some slides given to me by Digital Globe in the Caribbean. Here we identify density of sand, seagrass, and corals. Very important for habitat mapping. We did a small project in Manama where we mapped the seagrass, and this we sent divers down to ground truth our seabed classification, and we found that we were accurate in all the areas that we tested. The seagrass maps were identical to what we found on the seabed. What have you learned so far? There's a very large demand for this technology. We're the only company at the moment able to produce such fast and accurate seabed maps. Around 50% of the existing Worldview 2 library is usable, suitable to extract bathymetric data, which is fantastic, which means we don't even have to collect the data. You give us an area, we get the data from the library, we can create the bathymetry. We now understand the additional parameters for new tasking of satellite data. When we put these additional parameters in, there's a 90–95% chance that the information will be good to extract the bathymetric data. And improvements in the last year, we've learned a lot in the last year. We started a year and a half ago with very little knowledge or understanding of how we were going to bring this product to the market. Now we've got very fast production cycles. We can deliver 1–200 square kilometers in 2 or 3 days. We understand the parameters for imagery collection. We can do 5,000 square kilometers a month of processing, and we can scale that to 10,000 square kilometers a month with the addition of some additional computers and some people. And the height accuracies, our holy grail, what we want to achieve is the International Hydrographic Office Order 1B. This will allow us to use our data for charting. Thank you very much for your time. Thank you.
Anyway, very interesting publication. Yesterday, I presented the results of a United Nations joint ISPRS study on the status of mapping in the world. And at that time when I presented it, there was the director of the IHO there. He said, the mapping of the coastal areas is terrible. We almost have nothing. My question, would your company be able to help us in this ISPRS United Nations study to find out what mapping of coastal areas is available and how it could improve?
Yes, because that's a very big task, but we would like to explore the possibilities of working in that area. We are working alongside UKHO and other hydrographic officers, and these would be a great influence on that kind of product. Okay, I'll give you my card, sir. Okay. Thank you.
How do you think, would that be possible to apply these technologies on internal water flows? Can you hear me? Как на озера?
Rivers and lakes, yeah, okay. The rivers and lakes have to be clear, relatively clear water, same kind of parameters as the sea. Where a lot of the lakes around the world have a lot of vegetation and a lot of organic matter inside. If we were to do rivers or lakes where the water is clear and there's high reflectance from the bottom, then yes, we can do. But we don't market this kind of area because it's very difficult to do. But I wish we could. I wish we could.
Еще вопрос.
Another question.
Sorry, I didn't understood. Are you using stereo images from Worldview 2? Stereo images?
I can't hear you.
No, you're just classifying. Is that so?
Can't hear.
Ah, you can't hear.
No. This is a very good question, and I think the academia around the world are talking about this. Is the future in photogrammetry and stereo, or is it in mono? We're using, it's reflectance information that we're using the different bands. Basically, we calculate the depth of the water column. The reds are stopping at the top, the other bands are going through to the seabed. There's two different, we believe in the reflectance going forward, and we're very excited about Worldview 3 coming online next year with the hyperspectral data, because this could improve the models, the atmospheric models, and maybe the sea models as well, for us to be able to work with. So we've not worked out to put ground control points on the seabed yet, so...
Я прошу прощения, вот сейчас еще вопрос Миклаша, и потом мы перейдем к следующему. Да.
Very short question.
Yeah.
Probably I missed something. You mentioned several times the LiDAR.
Yeah.
Я, к сожалению, не слышу вопроса, потому что нет микрофона.
Yeah, yeah, yeah.
And two seconds depth, it concerns to the LiDAR.
LiDAR is between 1.8 and 2.4 times Secudisc. We average around about the same, maybe a little bit less, between 1.7 and 2.3. We average it out at 2. Yeah. Okay, thank you.
Спасибо, давайте поблагодарим.
Okay, thank you very much. All other questions will be asked later. Unfortunately, we are pressed for time.